Welcome to our astronomy class. This is week 3 of our classes. Last class, we looked at some basic ideas, namely, you go out at night, you look up at the sky, what do you see? The main takeaway there was, whatever we see, we're looking through the atmosphere, that layer of gases surrounding the Earth. And that layer of gases can change what we see. It can make the sky look blue. It could make a low moon look orange. It could make stars look like they're twinkling. Unfortunately, none of those are 100% accurate. The moon is still there. Stars are still there, but they don't have that appearance. So we have to keep in mind that when we look out into the sky, there are some deceptive things accidentally just because the light is passing through the atmosphere. In today's class, we're going to look at the first 3 planets in the solar system, and we're going to combine the idea of just talking about those first 3 planets with a little bit of physics and a little bit of equations, but hopefully that will be painless. So, for the solar system, the inner solar system. I'm not using the word inner in any scientific sense. There's no definite rule that says, well, these are the inner planets. I'm just using the word inner to mean the ones that are closest to the sun. So we have the sun here. Then we have planet Mercury. Planet Venus. There is no meaning to where I put them, like as of today, for me it's February 10th, 2020. I'm not saying, well, Venus is here and Mercury is there right now. I'm just putting them someplace. And then we have Earth. Again, I'm just putting them in here somewhere. And they're orbiting the sun. This is the direction of motion. Key question, and this is something that comes up a lot when we talk about things out there in space. Words like up and down, clockwise and counterclockwise become a little tricky to define. Here on Earth, I'm standing on the ground. Up is generally considered to be opposite of gravity. Gravity is pulling me down, so up is away. But if you're out in space and there's very little gravity, which way is up? It can be considered arbitrary. On the Earth, it's not arbitrary. Up is that way. Down is in the direction of gravity. But if you're out in space, up and down become a little bit harder to define. Along with this question, does the Earth go around the sun clockwise, in the clockwise direction, or the counterclockwise direction? I'm showing it here, these 3 planets, and they all go around, all the planets go in the same direction. They're all going counterclockwise. Is that indeed the direction of orbit? Doesn't matter. Depends on where you're looking from. For example, right now, me, I'm going to point to my right. That's my right, this way. If I turn around, That's my right. So is the direction to the right this way or the direction to the right that way? It could be either one. It depends on which way you're looking. Same is true for clockwise and counterclockwise. I'm just going to, on a sheet of paper over here, and I'll be right back to you. On a sheet of paper here, I'm just going to draw a curved arrow. This curved arrow is going in the clockwise direction. So if I look from here, that's clockwise. If I turn the paper around, if I flip it over, this same arrow is now going counterclockwise because now it's going this way, counterclockwise. So, simple question. Is this arrow going clockwise or counterclockwise? Well, for you looking at it from the front, it's going clockwise. For me looking at it from the back, it's going counterclockwise. It's the exact same curvy line. There is no right or wrong to saying which way it's going. Depends on where you're looking from. So, back to the solar system here. I'm showing them going this way. Is that really the direction they're going? Sure. But if I look from the other side, just like this, if I look from the other side of this paper, it's going to look like it's going in the opposite direction. So don't pay too much attention to clockwise or counterclockwise for the solar system. Depends on where you're looking from. So this is the basic idea. The Earth goes around in 1 year, 365 days. The other planets, we can look up how long they take to go around. Mercury goes around the sun in roughly 90 days. But again, it's not a big deal. There's lots of information about the planets we can look up. We're just looking at the concepts here, the ideas about what's going on. Planets orbit the sun being a star. Now we're going to look at an idea that's common to both the Earth and astronomy. And that's the idea of gravity. What is it? It's a word all of you have heard, probably many, many times, but I'm going to ask you and take a moment to answer. What is gravity? Well, a lot of people say this. Gravity is what holds things on Earth. Gravity is what pulls things down. If I take this eraser and let go, it falls down. That's because of gravity. So gravity is what pulls things down to the Earth. Well, what about the moon? Is there gravity on the moon? The moon's not the Earth. Is there gravity there? The answer is yes. If I was on the moon and dropped this pen, it would fall down too. Not as fast as here, but it would fall down. So when we talk about gravity, we can't just restrict ourselves to the Earth. The more proper definition of gravity is it's an attractive force between any two masses. It's usually only noticeable if at least one of the masses is large. In other words, if you had two small masses, you probably wouldn't even notice gravity. At least one of the masses has to be large. So let me put that down. It's noticed if at least one of the two masses is large. All right, so we're down a little path here talking about what gravity is. We said some words. We want to quantify this. Now, there's not going to be a lot of math in this course, but there will be some. We want to quantify gravity. In other words, come up with a number that can describe it. So what we want is a formula to find gravitational force. I'm going to put it down. Usually at this point, most students have not seen this formula before, but I am going to put it down. We're going to do an example with numbers. The force of gravity is given by this. I'm going to write it all down, and then we're going to come back and look at each step. 6.67 times 10 to the minus 11. That's a little bit of scientific notation, which you should have done before this. Maybe a little bit rusty, but you should have done it before. So it's this number with these units. I'm going to come back to these units. Newtons, meters squared over kilograms squared. I'm going to come back to this. Times mass 1 times mass 2 over d squared. Now, I want to set this up. What does all this mean? Well, gravity is an attractive force between two masses. So I'm going to say, here's mass 1. Over here is mass 2. And they're separated by a certain distance, d. The gravitational force between these two masses is given by this number times mass 1 times mass 2 divided by d squared. Of course, you do not have to memorize that. That's the formula for the gravitational force. So we have mass 1, we have mass 2, the separation. Just these units, the N, the M, and the kg. I'm going to leave this formula on the board. The letter N, that N. N stands for Newton. It's the unit of metric force. For most people around here, when they talk about force, they're going to talk about pounds. Like I'm pushing on the table with 20 pounds. I buy a 5-pound, actually they change it, a 4-pound bag of sugar. We usually, for people around here, we talk about pounds, but in the metric system, it's newtons. A newton is about 1/4 of a pound. That's an approximation. So we have this N for newtons. M you should know. M is the distance of a meter. And D, I'm sorry, not D, kg. We're talking about these units. N is newtons, M is meter, kg is kilograms. And what we wanted to do here was dissect or take apart or look at more closely. What is all this stuff? M1 is one mass, M2 is the other mass. D is how far apart they are. There's always going to be this 6.67 stuff in the front, so we're just going to leave that alone, except for the units. Newtons, which is the force, M is a distance, meters, and kilograms is the mass. What we want to be able to do is to use that formula to find the gravitational force. You don't have to memorize it, but you should be able to substitute numbers in. Let me put some numbers. Suppose mass 1 is 1 kilogram. And suppose mass 2 is 10 kilograms. And suppose the separation between these two is 100 meters. So we have two masses, we know the masses, separated by a known distance. What's the gravitational force between them? Now, we know gravity is an attractive force, because that's what we said. Gravity is an attractive force between any two masses. It's just the way Mother Nature behaves. You have two masses, there's automatically an attractive force. So there's a force of gravity pulling this to mass 2, and there's a force of gravity on mass 2 pulling it to mass 1. They're attracted to each other because there's two masses. They're going to attract each other. And if you just left them alone, if there was nothing else in the entire universe, what would these two masses end up doing? They'd crash into each other because there's a force pulling them together. They'd crash into each other. That's the natural consequence of attractive forces. Things will be pulled together. What we want to do is find the force. And we're going to find it in units of newtons. And is it going to be 10 newtons, a million newtons? What is it? We have the force of gravity. Equals 6.67 times 10 to the minus 11 newtons meters squared over kilogram squared. I just copied that exactly. Times mass 1 kilogram. Times mass 2. (10 kilograms). At this point, I want to say that 1 kilogram and 10 kilograms, those are small masses. 1 kilogram is about 2 pounds. So if you pick up something that weighs 2 pounds, let's say a big heavy book, a book that weighs 2 pounds, that's about a kilogram. 10 kilograms would be about 20 pounds. Not exactly, but roughly 20 pounds. So if you had a 20-pound bag of rice, that's 10 kilograms. In terms of planets and stars and moons, this is ridiculously tiny. There's no planet that's 1 kilogram, not even close. We're just doing this as an example using numbers, and there'll be practice for you using this formula here. Then we have D, which is a separation. We're told that's 100 meters. And it's squared. So we're going to do the arithmetic. It's this times this divided by this. Now, I'm not going to write it out all over again. This is something you can do simply using your calculator, which you should be familiar with. Of course, using your calculator, you should be familiar with scientific notation, which is what this is. And when you do this arithmetic, you should get 6.67 times 10 to the minus 14 Again, I just took my calculator and I did these numbers, not forgetting that that's squared, that denominator. And for the units, the kilogram squares cancel, and the meters squared cancel. The only unit left is Newton. So, the gravitational attractive, I don't really have to say attractive because by definition gravity is attractive. The gravitational attractive force between these two masses is a number. What number? This number. That is a really tiny number. Because 10 to the minus 14, I'm going to ask you folks the question, what does that 10 to the minus 14 mean? It means this. It's 6.67 times 10 to the minus 14 newtons, which I'm going to just call n. The minus 14 means the decimal point goes back to the left 14 places. 1, 2, 3, 4, 5. I'm not going to draw them all in. So the force is going to be a whole bunch of zeros and then 6, 6, 7. In our everyday world, that's going to be a tiny, tiny force. But that's what we said earlier in class. This idea of a gravitational force only becomes noticeable if one of the masses is, at least one of the masses, is really, really big. Like big the size of a planet. Not big the size of a car, but big the size of a planet. So what we've done is we've defined what gravity is. We have an equation for it. And now we have a way to answer this question. Well, this thing has this much mass, this thing has that much mass, they're this far away, what's gravity pulling them together? That equation we had is the answer. That's Newton's universal law of gravitation. If you've taken physics 1, if you've taken physics before, you know about Newton's laws probably, like for every action there's an equal and opposite reaction, as one example. Well, that same scientist who came up with for every action there's an equal and opposite reaction also came up with this idea of universal gravity. There's an attractive force between any two masses. So this is like a baby example, because this is not a real question in astronomy. Those masses are way too small. But if we graduate from that baby astronomy question to something that's more with what's going on in the solar system, we could have this. Here's the sun. Here's the earth. This is not drawn to scale. I'm just drawing circles to represent the sun and the earth. It is not to scale. If it was to scale, the earth would be way, 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 way far away. And it'd be a lot smaller than in this diagram. But it's just showing there's the sun, there's the earth. The sun has a mass, which I'll write down. The mass of the sun, if I put a circle with a little dot in it, that's the standard astronomical symbol for the sun. The mass of the sun is about 2 times 10 to the 30 kilograms. It's really big. The earth is not as big as the sun. I mean, I drew it that way on purpose to illustrate that. The mass of the earth is about 6 times 10 to the 24 kilograms. Big compared to a car, but not very big compared to the sun. The sun is by far the biggest thing in the solar system, both by diameter and by mass. So I have one mass, I have another mass. They're separated by a distance. The distance now I'm just going to put a number down. The number varies because the Earth does not go around the sun in a perfect circle. But I'm going to put down a number because we want to say something. The distance from the sun to the Earth is about 143 million kilometers. That's a big distance. And because there are two masses, there's going to be a force of gravity, which I'm going to draw in. The mass of the sun is going to be attracted to the mass of the Earth. And the mass of the Earth is going to be attracted to the mass of the sun. That's fitting into what our definition of gravity is. There's an attractive force between two masses. Masses want to be pulled together. We could calculate the force of gravity. We had the formula, that's 6.67 times mass 1 times mass 2 divided by how far apart they are squared. We have all that information. We're not going to do it, though. You can do that for practice, for homework, but it's just taking these big numbers. This 10 to the 30 means the decimal point goes 30 places to the right. So depending on when this number here is positive or negative, if it's negative, the decimal point goes to the left. If it's positive, it goes to the right. Mass of the sun, mass of the Earth. I should put in the symbol for the Earth, which we did look at last class. The symbol for the Earth is a circle with this kind of a cross in it. This means mass of the sun. That means mass of the Earth. And we could calculate the force of gravity. Now, since these are such big numbers, the force of gravity is going to be really, really big. I'm just going to leave it like that. It's going to be really big. So let me erase this and just leave the Earth and the sun. And I'm just going to show the gravity. I mean, technically, the Earth is being pulled to the sun's being pulled to the Earth. But since the sun is so much bigger, the sun is like 1,000,000 times more massive than the Earth. Since the sun has so much more mass, the sun really is not going to get pushed around. It's just so big. It'd be like me trying to push a plane around. I can't. The plane has so much more mass than I do. Well, the Earth has so much more mass. Sorry, the sun has so much more mass than the Earth. The sun's not going to get pulled around. The Earth, maybe. But we can ask this question. If you just saw this picture and you said, oh, that's interesting. There's a force pulling the Earth to the sun. Why doesn't the Earth crash into the sun? I mean, it should, Earlier in this class, we said if you have two masses and leave them alone, they're going to get pulled together and crash. Here's two masses. They should get pulled together. The Earth should crash into the sun. It doesn't. It hasn't. The Earth has been out there with the sun for about 4.5 billion years. You would think, well, if it hasn't crashed into the sun in 4.5 billion years, it's probably not going to crash into the sun. That's a reasonable statement. The Earth is not going to crash into the sun. But we have how do we explain that? I mean, there is a force pulling the Earth towards the sun. Why isn't it going to crash into it? Now, if you think about it, what could be a possible explanation for why the Earth is not going to crash into the sun? The only possible answer is something else has to be going on. If this picture was 100% accurate, the Earth would be crashing into the sun. But it's not. Something else is going on. We've mentioned the something else already today and last week, and you knew it even before you took this class. The something else that's going on is the Earth is orbiting the sun. The Earth is not sitting still. It's moving. It's going around the sun. Again, I'll say, if the Earth was standing still, it definitely would crash into the sun. But it's not standing still. Once a year, it goes around. That's the definition of a year. It takes the Earth about 365.25 days to make a trip around the sun. So it's orbiting. That's the missing link. So the missing link is the answer to this question. If there is a force of gravity, why doesn't the Earth crash into the sun? We said there's only one possible way out of that problem. Something else got to be going on. The something else going on is the Earth's in orbit. All orbital motion causes a new force called the centrifugal force. So anything in orbit around the sun, there's a centrifugal force that's directed away from the sun. It's not magic, but I'm going to say magic. The magical answer to the question, why doesn't the Earth crash into the sun, is because the Earth is orbiting. And if it's orbiting, there's a new force involved, centrifugal force, that's directed away from the sun. So I'm just going to show an arrow directed away from the sun. And I'll just abbreviate that with the letter C and then fugal for centrifugal. So there's really two forces acting on the Earth. Gravity trying to pull it into the sun, and centrifugal trying to throw it away from the sun. And now we're going to say something really important in astronomy, because there's billions of things that orbit. I'm going to come back to the board in a moment. The Earth orbits the sun. So does Mercury. So does Venus. So does Mars. So does Jupiter. So does every asteroid. So does every comet. There's lots of things orbiting the sun. They're all in orbital motion. There's nothing that's just sitting there. So if I say, well, here's the sun, and here's this big old asteroid sitting there. Wrong. Nothing is just sitting there. everything is going around the sun. And if you take the Earth's moon, you can say, well, here's the Earth, here's the moon, two masses, the moon should crash into the Earth. No, it's not, because the moon goes around the Earth. More orbital motion. The planet Jupiter has over 60 moons. And moons are just things orbiting a planet. It has over 60 of them. Why aren't they all being pulled into Jupiter by Jupiter's gravity? Answer, because they're orbiting. There's lots of orbital motion in the solar system. For a stable orbit, meaning that it just kind of keeps going by itself. Now, we're making some simplifications here. They don't last forever, but I'm going to say almost forever. Go around and around. For a stable orbit, the amount of the centrifugal force is equal to the amount of gravitational force. This is a very important statement for how the solar system behaves. For any stable orbit, the centrifugal force pushing away from the sun is balanced by the centrifugal force pulling towards the sun. So there's always two forces going on here. That's true for anything in orbit. We have a formula for gravitational force that 6.67 times 10 to the minus 11, and so on. We now want to get a formula for centrifugal force, which we will. Here is the sun. Here's the Earth. The Earth is going around the sun. The Earth has a velocity. It has to, because it's moving around the sun. If it's not moving around the sun, it's not going to orbit. The Earth has a mass. Let's call it M1. I could call it anything I want. I could call it M2 if I wanted, or just plain old M. I'm going to call it M1. And it's going around in a circle approximately. So from the sun to the Earth, there's a radius, which I'm just going to call R for radius. And we're going to say this. Because of this orbit, there is a centrifugal force. And I am thinking, you probably know by now that physics or mechanics or weight and balance or dynamics, these are a lot of equations to describe things. Equations are valuable because you can use measurements in them. Just to say, oh, you know what, there's a force between the Earth and the sun. Not good enough. It's somewhat good, but I need a number. Is the force 1,000,000 pounds, 1,000,000,000 pounds, 100 pounds? I need to know numbers. I mean, sciences make progress because of numbers. This cell phone would not exist if people just said, oh, that's interesting. I can use a battery to light a flashlight. Let me make a phone out of that battery. No, it's a lot more complicated than that. People use all kinds of measurements to figure out how to make a cell phone. Here, we want to use all kinds of measurements. Not to scare you away. It's not going to be every class, all measurements all the time. Sometimes there will be measurements. There's a measurement for centrifugal force. The force centrifugal is given by the mass. So we call this mass 1 for the Earth, times its velocity. I mean, it has to have a velocity because it's going around. It's definitely moving. Times its velocity squared divided by the radius. So we had a formula for gravitational force. Now we have a formula for centrifugal force. Both of these formulas have been around for hundreds of years. People were clever enough to figure this out a long time ago. And I'm going to erase this. And go back to one super main formula. For a stable orbit. We said the force of gravity is equal to the centrifugal force. Things have to stay in balance. That's going to keep the force pulling the Earth into the sun balanced by the force trying to pull it away. They stay balanced. Gravitational force, we had said, is 6.67. This is something we've seen before. Newton meter squared, kilogram squared, times m1 times m2 over d squared. That's what we said with the force of gravity was. And now on the right-hand side of the equation, centrifugal force. It's that new one I just put on the board a couple of minutes ago. Mass 1 times v squared, the velocity of the Earth as it orbits the sun, divided by r, where we said r represents the distance from the sun to the Earth. But that's what d is. D is also the distance from the sun to the Earth. You could call it any letter you want. If you want to call it L, you can call it L. But for our purposes, we're calling that distance from the sun to the Earth d. The Earth goes around at distance d. So I'm just going to put d down here, where d is the distance from the sun to the Earth. It's going around at that distance. M1 is mass of the Earth. M2 is mass of the sun. By the way, we put both of those down earlier today. And v is the velocity of the Earth as it orbits the sun. This equation here controls orbital motion. And there's a lot of orbital motion in astronomy. The physics of orbital motion is the force of gravity pulling things together is balanced by the centrifugal force. Now, there's two more things we want to say for today. First, we want to define the word circle. It's a common word. All of you know it very well. But if you're asked to define it, other than saying, well, it looks like this. No, I'm not interested in a picture of a circle. I just want to know, what does it mean? What is a circle? A mathematical answer is this. It's all points equidistant from one point. The definition of a circle is all points that are equidistant from one point. So let me put one point here. Let me put an X through it. Equidistant means the same distance. Suppose I say, I want all the points that are 10 inches away from that point. So I could come over here and say, you know what? This point is 10 inches away. There's one over here that's 10 inches away. One over here, 10 inches away. One over here, 10 inches away. One over here, 10 inches away. And I can get a whole bunch of points that are 10 inches away. And if I kept on filling in all the points that were 10 inches equidistant away, that's not a very good circle. But you would end up with a, let me try and make it a little better. You would end up with a circle. It's all the points equidistant from one point. That's the definition of a circle. Now, I could use a piece of string. I don't know how well you can see this. There it is. I can come closer. Here's a piece of string. I can use a string to draw a circle, not freehand. I can take this string and a piece of tape, and I could tape one end down to the board. So here's a string, one end's taped to the board. From this point where it's taped or held down to the end, that's a certain distance. From here to here, say it's 8 inches. So I could go 8 inches in this direction, 8 inches in that direction, 8 inches in that direction, 8 inches in that direction. All points equidistant. If I take my board marker and I just poke it through, I tied a little knot in the string. I poke it through the little circle that results from the knot. So there's an opening here, a little loop. And I keep this pen so that it pulls the string tight. I'm 6 inches away, 6 inches away. All these points are the same distance. And if I actually draw them in, you get a much nicer circle. That's it. That's the definition of a circle. All points equidistant from one point. The one point is here, right in the middle. Forget about this piece, that's doing nothing. But I took all the points the same distance from that middle point, and that's the definition of a circle. Let me get this off the board. Now we can say, hey, you know what? Let me put the sun in the middle. Instead of that cross, let me put the sun in the middle. I can say here is the sun. And here's the earth. And the earth goes around the sun. Now, I'm going down a nice little path here saying, oh, this is nice. The earth goes around the sun in a circle. That's not 100% true. The earth does not orbit the sun in a circle. That picture is not really accurate. It actually orbits in an ellipse. You should have heard that word in math classes. It's like oval shaped, like an egg, not a perfect circle, but in some very loose sense, roundish. The earth orbits in an ellipse close to a circle. But not actually a circle. Important statement. The earth does not orbit the sun in a circle. It orbits the sun in an ellipse. Oval shape. So let me put the sun back on the board. Let's say here's the earth. In the real case, the earth goes around in an oval shape. Again, I'm drawing this freehand. So it's kind of like flattened out circle. So the distance from the sun to the earth varies. Sometimes the earth is a little closer, sometimes it's a little further. it's a big distance. It's about 93 million miles. But it's not always the same. Again, sometimes it's closer, sometimes it's further. There's a definition here. The average distance from the sun to the earth is called an astronomical, let me spell this correctly here for you, unit. Because it's not a circle, because sometimes it's closer and sometimes it's further, we can calculate the average distance from the sun to the earth, which gets an important name in astronomy, an astronomical unit. So it's called 1 AU. The average distance from the sun to the earth is 1 astronomical unit, 1 AU. So this is our class for today. A little bit mathy, a little bit on the math side, but it's important to set up this groundwork because we're going to use it again and again. We defined what gravity is, attractive force between any two masses. We said, well, if there's an attractive force between any two masses, why doesn't the Earth crash into the sun? And we said, well, there's got to be some answer. And the answer was centrifugal force. And for a stable orbit, the centrifugal force balances out the force of gravity, so things stay in orbit for a very long time. We said, well, people say the Earth goes around the sun. Is it going around in a perfect circle? No, it's not going around in a perfect circle. It's close to a perfect circle, but it's not exactly a perfect circle. It's more of an ellipse. And then we come up with an important measurement in astronomy. If somebody said, how far is the Earth from the sun? Well, today it's this number, tomorrow it's going to be a different number, and a month from now it's going to be a different number because the distance varies. It gets further away, then it gets closer, then it gets further away, then it gets closer. So if somebody said, well, how far away is it? We can say, well, you know, the average distance from the Earth to the sun is about 93 million miles. There's a name for that. It's called an astronomical unit. So, saying the question one more time. How far away is the Earth from the sun? The answer, you can say 1 AU, or 1 astronomical unit. So, this is our class for today. For me, it's Monday, February 10th. You'll probably be getting this on the 11th or the 12th of February. There'll be extra readings posted on D2L. There'll be homework questions posted on D2L because this class, since it involved math, there will be some practice questions where you'll need your calculator to get the answer. So, thank you so much for your time. If you have any questions, please let me know. If you see me, please stop me and ask. You can watch this tape as many times as you like. Again, I realize this might be a little bit tricky for you because we got into some calculations and we also got into scientific notation, which you may be a little bit rusty with. But that's fine. There's nothing wrong with that. Just practice up a bit. Make sure you look at D2L for additional reading and practice questions. Thank you so much for your time. Have a good day. Happy Valentine's Day to all of you, and I'll look forward to seeing you next class.